So who am I? Well, what do I mean, I identify as a computer programmer. I work for Grafana Labs, hence the shirt. And I work on the backend databases, storage of metrics, logs, and traces. And incidentally, Donya, who gave the previous talk, for those of you who were here, wanted to talk about hosting some metrics in the cloud. So I know a service that does that, and Grafana Cloud has a generous free tier. You can store all of the metrics from your henhouse and 9,998 more. Anyway, so enough of that. I optimize code. I'm forever wanting to make it go faster, or even just saying, like, why is it so slow? Why? What is it doing? In fact, that's why I work in observability, because I care about that all the time. What else? A message. I made a few rules for myself. Actually, from the keynote, constraints are helpful when trying to think of what to do. So I'm not going to talk about anything unsafe in the very specific Go sense of the word. I am going to put a lot of code on the screen, and I hope I don't lose everyone. I guess, if you are getting lost, we've got an hour, right? So if I totally lost you 10 minutes in, then, I don't know, scream at me or something, because hopefully I can explain it a bit more. And anyway, let's hope that works. What else? Yeah, what are my other constraints? Like, what is an obscure optimization? How does one pick one of these things? So my rules, my constraints were that it's must be something that does not appear in the popular tutorials for Go performance. So I specifically scanned Dave Cheney's one and Damian Greisky's. Oh, that is not so good. Looking at AV at the back, we sort of lost the feed temporarily. Well, so there are those tutorials, and what I'm going to talk about is none of the things I'm going to talk about are in any of those tutorials. What else? How else did I get? I asked colleagues. I said, what do you think is an obscure optimization? And that's kind of where the previous rule came in, like nothing unsafe, because most of what they came up with was unsafe. Sorry, I'm just pausing while I'm not getting any hints from the back, so let me see if I can make the screen do something different. Okay. Must have been my fault. Okay. Okay, we're back. So let's start. Blowing my own trumpet slightly. This is a change that is in Go 1.19 to the regexp library, which I made. It's not in the release notes, which I'm slightly aggrieved about. So I needed to come here to tell you. And so the good news is all of your regexps are now faster. Yeah, you're welcome. The other point is that this, by my rules, this is not an obscure optimization. I mean, it's kind of cool that where's my mouse? Here. So the whole optimization consists of adding one character. And what it does, instead of copying this value, it takes a pointer to it. And the whole thing goes, on my laptop anyway, goes 30% faster. But I don't think this is obscure, right? Because it's just that nobody had looked there. The exact process for finding this consisted of running the profiler and looking for lines that were higher than other lines, and then wondering what was going on there. So yeah, I wanted to mention this, so at least you have something to take away, right? You just upgrade to Go 119 and your regex will go faster. But I think this is not obscure. It's just that nobody had noticed it before. Anyway, let's get in. So the first one I do want to talk about is a change I made in Prometheus. A few, I don't know, 4 months ago, something like that. This is a function. The function is called ensure order. It gets called during startup. Prometheus, you start up Prometheus, it reads in everything it was doing when you last shut it down. And then it wants to ensure that its indexes are all in order. So it basically calls sort on everything. And when you run the benchmark for this, what stands out, well, so this can take several seconds, which is why I wanted to speed it up, because you don't want your Prometheus to just do nothing for several seconds. It is allocating, in the benchmark, it's allocating 1 million times per operation. So another of my messages to take away, memory allocation, almost always kills performance. In fact, it's almost not worth looking at anything else to a first approximation. This is one of my rules. It's always memory allocation. So yeah, why is this thing, the data's mostly sorted already, because when it shut down last time, it was mostly sorted. Well, it was all sorted, actually, when it shut down. So when you fire it up again, it should still be sorted. OK, well, hopefully we know how to repair this. Sorry, the screen's gone again, for those of you following along. OK. Yeah, so why is it, the data's almost all sorted. We're calling sort, which doesn't do a lot of memory allocation if it doesn't have anything to do. And why is it allocating 1 million bits of memory? So what do? We fire up the profiler. We're getting AV advice here. So would it be easier if I did mirror the screen? I'd rather be able to move the mouse around. If I mirror the screens, would it work better? Because you don't know. All right, well, let's carry on. Yeah, so run the profiler, because we're trying to figure out what's going on in this program. And I don't know about you, but I can't understand these pictures. I have absolutely no idea what's going on when this comes up on the screen. So I do this way. This is the flame graph view. And it's much easier to understand. So the basic idea here is, let me get my mouse in the right place. Right. So the width of the flame graph is 100% of your CPU, in this case, utilization. So the wide bars are the ones you want to look at, because they're taking the most CPU. So calling sort is taking most of the time, so that seems reasonable. But there's this other guy here, and in fact, I made a little cool animation so that I wouldn't forget to talk about this. 16% of all the CPU is in this mystery function over here, which is called conv tslice. So what is going on here? Actually, is this obscure? Does anyone know what's going on? Nobody's willing to admit it. OK, so either it's good or we have no idea. Yeah, so again, in the profiler, you can bring up a line-by-line view of the source, annotated with how long everything takes. So for instance, the this line that calls sort is taking most of the time. So fair enough. So that's not kind of answering this question about what is that conv tslice thing. Let me step back and talk about the code for a bit, and then we'll get back to what that function is. So we're calling sort, and sort takes a thing which is named interface, which is kind of unhelpful name in context. But it's sort.interface. It's the interface of the sort package, and what that means is it has to implement len, less, and swap. Those are the requirements of the sort package. That when you give it something to sort, that it has to have those methods. And the thing that we're passing in is a slice within the guts of Prometheus. So it's a slice of these series references. And we do a cast on it because it's kind of starts off as just a boring slice, and we need to cast it to the thing that supports those methods. Okay. Right, are we following along so far? So we're calling the sort function, we've got a slice, we cast it to this more interesting slice which supports those three methods. What is a slice? So under the hood, it's like a set of values one after another in memory. And the way Go implements it is it's three things. It's a pointer to the first one. It's the length, how many of those things have you actually got? And the capacity is how many could you have in this one block of memory. So that's a slice. What is an interface value? So I'm quoting here from a tour of Go. An interface value is two things, the value itself and its type. And so draw a picture of that. So each of those are 64-bit pointers. The value itself is kind of the interesting bit, but the interface value carries around this other pointer, which I'm again need to move my mouse. Right. So you've got the value bit and the type bit. And the type points off to some kind of metadata for the Go runtime. And for instance, that is exactly how to call the methods len, less, and swap. So that's kind of useful information. Now, I kind of learned this stuff in C++. And Java works the same way. So I just want to emphasize it is completely different in Go. In those other languages, what happens is the object itself has what in C++ called a V pointer that points off to the metadata and how to call the methods. So the object is kind of a different shape. It's got this special magic thing at the beginning of the object. And in those languages, you can't have methods on a kind of basic type like an int or just an array of values in C. Objects are laid out very specially in those languages, whereas in Go, the value itself has the type information with it. So interface values are two 64-bit pointers. Right, they're well, on a 64-bit machine. They're a different size on a 32-bit machine. But, oh, we lost the screen again. This is getting fun. Put it back there. Okay. Right, so this is a picture of what's going on in this bit of code. We've got the thing that we want is an interface value, which is going to be those two pointers. The value is going to point to the slice header, that thing with the three Sorry, this thing over here is the slice header with the 3 values in it. And then that points to the actual slice, which is down here. All right. So going back to the code, this is the same slide I put up a couple minutes earlier. We want to know, like, what is it doing? Why is it calling this other function? And why is it allocating memory? So if we switch over to the memory profile, which I tend to do, like I say, memory allocation is almost always the thing to look at. So that's what I tend to do first. And you can click on the line of Go code, and it'll expand it out to assembly code. And now we see this magic hidden function, and then it's annotated. So this line here, this is where all of that memory allocation is taking place on that one function. So what is it doing? It is making a copy of this thing, of the slice header. I didn't ask it to, but every time you cast from a slice value to an interface value, Go will call this function. It's hard-coded, right? I mean, it's doing it so that when you take the interface value and pass it to something else, it can't modify the value that you started with, because that's the sort of contract of pass-by value. And I'll show you in a minute. We can pass this thing as a pointer, and it won't do this. But if you want to pass, and this is very, very common, right? If you start with a slice, you cast it to an interface value, Go is going to do this magic little memory allocation for you. And if you do that enough, which is what happens in the Prometheus case, if you do this 1,000,000 times, it allocates 1,000,000 blocks of memory. And, well, we'll see what happens when we take it out. Okay, what are we going to do about it? That's the interesting question. So as I say, let's let's not cast the value, let's cast a pointer to the value. Because, sort is going to sort the slice anyway. We actually we're okay with it being modified. We want it to be modified. So there we go. We create a thing we can take the address of, which is the cast, and we pass that to sort. And what's happened is all of the memory, the same amount of memory, has moved onto the previous line. So now it's not calling conv tslice. What's happening now is this thing escapes to the heap. Anytime you pass a pointer through an interface, it has to live on the heap. So I've got a thing which is a local variable here, but it's on the heap. So every time around this loop, it makes another memory allocation. I'm actually no further on than I was before. It's just a different reason. So the real fix is to hoist this out the loop. So what I've done, I've just moved my local variable outside of the loop. And I do the same thing. I cast and I take the pointer to it. And so the program still works, but it's not allocating any memory. This is the profiler view. All of that gigabytes of memory has disappeared because it never needed to allocate it in the first place. It was just kind of doing it to be helpful. Success. So just to prove that, or this is the benchmark. This is from the PR that I posted. So this bit of starting up Prometheus, I mean, it depends on your exact data shape, but best case on the benchmarks, it goes 25% faster. So good. One interesting thing, the profile claimed that function, that bit that I pointed at, took 16%. And we took it out, the program went 25% faster. Is math wrong? So this is another lesson or learning that is, I think, really important. Memory allocation and garbage collection slows your program down in ways that are not obvious, in ways that don't show up on the profile. They're very subtle effects. Well, some of the more obvious ones are that the CPU data cache is having things knocked out of it by the garbage collector wandering around. If you don't allocate memory, then everything can stay in cache. If you allocate memory, then new things need to come into the cache all the time. This is in the hardware of the CPU. And the garbage collector, which is running in the background, is sort of busily destroying your cache. It's taking all the data that you do want to use and putting different data in the cache because that's what it's looking at the same time in the background. So yeah, this is very, very common finding for me, that you find a memory allocation that is slowing you down, you take out the memory allocation, and the program goes way faster than what was apparent to begin with. Definite tip there. Okay, next one. Let's go back to the profile. And I've expanded this, so this is after we put the fix in. I've expanded this one function to fill the screen so that it's kind of easier to see what's going on. And in fact, so calling sort is taking basically all of the time now. Well, I said earlier the data's almost entirely sorted. So, what if we did that instead? Or what if we checked if it was already sorted? That's probably easier, right? To check if it's sorted than to sort it every time. So, well, just draw attention. So this is like 20 seconds right now. Yeah, so change the code. Check if it's sorted first. Okay, now is sorted is taking all the time. It's gone down a bit, right? We were at 19 seconds before. We're at 14 seconds now. But it's a little bit disappointing that checking to see if things are sorted takes almost as much time as sorting them. So that's a bit, yeah, people trying to work out why that is, right?
Shouldn't sort be doing is sorted first itself?
Oh, yeah. So just the question was, does sort like check first of all? And the answer is no. The library sort function is written on the assumption that your data is not sorted and it's not worth checking. Because it would have to do like one extra pass through the data and say, oh, no, it's not sorted. So yeah, good thought. We might return to that thought. Does anyone know that one? No, okay. Mystery tour. All right, where are we going? Right, so is sorted is taking all the time. And if we look at a profile of that, where's my mouse? It's over here. Yeah, so most of the time is calling this function, which is the comparison function. This was from our interface earlier. So calling this function is taking most of the time, which I can see over here. Oh, yeah, just how to read this view. It says flat and cumulative. That's what that stands for. So the flat number, that's in this function, how long did it take? And then this one is this function plus all the ones that it called. And it's line by line. So doing the work of the less function takes about 1 second longer, but calling it takes most of the time. So not doing the work, calling the function is taking most of the time on this line. So that's a bit disappointing. So what's going on here? Well, actually, I didn't say what's going on here. I said, I bet generics is going to fix this, right? Because it's, well, frankly, because I used to work in C++, and they would have fixed it in C++. But no, it doesn't. This one is basically identical. In Go, a type parameterized method, let's not go on too far. Right. A type parameterized method, which we call in the same way, is implemented as an interface. It's implemented with those 2 pointers and the lookup of the method, and it's just as slow as it was before. So that's sad. Okay. Right. What if now we're not passing an interface, we're passing a slice. So that's going to make it easier, right? We're not doing everything through an interface. We've actually got a slice. And the slice is of values which support the less method. So yeah, let me emphasize. We're passing a slice now. We're not passing an interface. We're passing a slice. Well, so I've got a link at the bottom there, and I've not actually posted these slides online, but I'm sure they will go up. Actually, yeah, I'll tweet about it or something, or if I forget, then you should tweet at me. This one doesn't go faster. In fact, this one goes slower. And there's a whole blog that someone at Planet Scale wrote about why, which is incredibly detailed. I mean, fantastic work. But it's basically the kind of bookkeeping of generic methods. Anyway, Ian Lance Taylor, one of the Go team, said it more clearly. When you need something like a comparison, prefer a function, not a method. Okay, so what does that look like? So we're back to the profiler now. So the code has changed. So we're passing a slice in and a function, and calling that function. So this one is still 4 seconds to call the function, 5 seconds to do the work inside the function. But we're down. So the total, this number here before was like 19 seconds or something like that. We're coming down. It's getting faster. So that's good. It's it's still a bit slow. In this case, inside Prometheus, these values are basically integers. The series ref type is an integer inside Prometheus. And what I can do now is I can say I'm going to pass I'm going to parameterize this function by a type which is one of these things. And this, I didn't type them all out, but basically like int 32, int 64. Like if you list all the possible types that you can do less than on, then you can just write less than in this code. There's no method call. And finally, so that thing that was like 20 seconds before, or at least this bit of it was like 12 seconds, is now down lower than a second. Interesting learning. Generics most of the time make your code slower. Sometimes make it a lot faster. And the case where they make it a lot faster is where you're not using an interface. Not using, it's slightly confusing, sorry, just step back slightly. It's slightly confusing because the keyword is still interface, but it's not like a thing.thing brackets, not that kind of interface. This is kind of listing the types that I can use in my generic call. And because I'm not calling a method, calling methods is the slow thing. it is incredibly fast. Good. Okay, so you don't have to type all that code in because it's in a package which is called slices. I mean, essentially, this is a standard library package called slices. But the Go team are not ready to move it into the standard library. So right now, you have to import it as golang.org/x/exp/slices. The exp stands for experimental. Yeah, it's experimental because in the sense that it's not subject to the Go compatibility guarantee. They could still change this before it goes into the standard library, but they probably won't. I mean, it's pretty simple. So both of those functions that I looked at are in this package, the ones that go a bit faster. Sorry, and the one that goes a lot. So this one goes a bit faster, passing in a function. This one went a lot faster because we could directly compare. So if you have a slice of ints or a slice of strings or something like that, you can, with this package, you can run isSorted a lot faster. Even better, you can call sort on those things, and it goes also just as fast because they have a new sorting algorithm in this package, which is going to go into Go, probably 1.20, maybe 1.21. Our sorting algorithm is called PDQ sort, which I guess is a pun, right? So the old one is QSort, quick sort, and this one is pretty damn quick sort, or I don't know. But PDQ sort has the behavior that it is blindingly fast on already sorted data. So the idea that Ilya here had, in fact, comes true. That the new sorting algorithm is much, much faster on already sorted data. So in fact, this is the one I submitted to Prometheus, which takes that benchmark down to virtually nothing, which, as far as I know, has not been reviewed yet. Any?
They would be slower if there were methods on E, right? So
yeah.
Was method on E.
Yeah. So these, yeah.
But it also has to be part of the package, so we don't know what E's may be.
Yeah. So the ones isSorted and sort only work on int, float, string. The ones where you can do less than. And the ones where you pass in a function, you write the function, you write the less function, so it can be anything. And it turns out, because of the overhead of calling functions, that the ones where you don't pass in a function are much, much faster, but only on the subset of types. Okay. Breathe. I thought I'd just like to put in a little pause here. Is anybody, are we okay? We're doing good? Okay, good. Where am I? I must be like 2/3 of the way through or something. Let's, another shout out. So this is a talk at a previous GopherCon. By Eben Freeman. It's a few years back, but you can find it on YouTube. And he gives a lot of information about the memory allocator, the garbage collector, which I certainly found very illuminating. That's one of the reasons why I do these talks, by the way, is I learn a lot. Because it's very easy to submit the title, yeah, I'll do a talk. I do this all the time. I work. This is what I do. I optimize things. I know what I'm talking about. And then I get halfway through the slides, and I think, well, why does it do that? I don't know. Anyway, so I learned a lot from this talk. the garbage collector. I'm going to talk about the garbage collector now, so I just wanted to shout that out. There's a lot more detail in there. I want to kind of touch on some high points, and one more thing that you can try at home, and then we'll be done. So I'm going to kind of refer to this concept a lot, and I usually do it by kind of waving my hand around like this. This sawtooth pattern is naively how the garbage collector works. So memory is allocated, it piles up, and then the collector frees all the memory again. Well, not all of it, probably, a little bit left over, but piles up, freeze, piles up, freeze. Right, that is fundamentally what's going on inside the garbage collector. And the activity of figuring out what can be freed is the expensive bit. It involves walking every pointer in your whole program to see what it points to, because anything that has a pointer either to the beginning of the object or somewhere in the middle of the object, the whole object has to stay alive, has to be not garbage. So this is a fantastic amount of work, especially if you have like gigabytes of memory. The garbage collector has to walk every pointer in everything across your whole gigabytes of memory. So that is a lot of work. So that is why, by avoiding memory allocation, we slow down that slope. We flatten the slope. We slow down the rate of memory allocation, so the garbage collector runs less often, so it slows your program down less, right? That is why saving memory allocation is a good thing. But there's, what if you can't do that? What if it's kind of fundamental to the operation of your program that it's allocating memory, or perhaps more likely that you're calling a library that just won't stop allocating memory, gRPC mentioning no names. Well, what you can do instead is allow the heap to grow more. So this is maybe a little bit counterintuitive, but the goal, the number one goal, is to garbage collect less and less often. So if we run the program with a bigger heap, it will run the garbage collector less often, and the program will go faster, right? So this is obscure, hopefully. There's a technique for doing this, which, who's heard of heap ballast? Maybe 5%, okay, cool. Fairly obscure. This is not the thing, right? This is the old thing. I'll show you the new thing in a minute. This came out of a blog post from Twitch, so basically what we do is we allocate, or we kind of pretend to allocate a big block of memory at program startup. And so what the Go garbage collector sees is a bigger heap. And in fact, the way it works, the way the Go garbage collector works, is it says whenever I get to the bottom of this, wherever I get to here, after I've freed all the garbage, I will allow the heap to get twice as big before it comes down again. And it sets that as a target, actually. So that is why adding a fake memory allocation means that the heap gets bigger, and will slow down your garbage collector, and that works. I'll show you some kind of examples in a minute. And the reason why this is worthy of talking about and writing blog posts about and so on is there was no other way of getting Go to use a bigger heap. Right? There's a tuning parameter called GoGC. You could sort of change the relative, you could change the ratio between here and here, but you couldn't say, please just use a bigger heap. I bought the memory, use it. You couldn't say that. So that is why heap ballast was a thing. All right, so I wanted to run some examples to kind of illustrate what's going on. So, so I wrote a function, and I wanted to kind of have a fake server that did some work and hopefully allocated some memory. And so what I did was I implemented the Fibonacci function by concatenating strings. So the Fibonacci function, each number is the sum of the two previous numbers. So values in this universe are encoded as lengths of strings, which is an incredibly inefficient way to encode numbers, but it's for science. Yeah, this is, so hopefully you can see what it's doing. It's taking one character less off the front of the string and concatenating that with two characters less off the same string. So that's the two previous numbers in the Fibonacci sequence. And then, if it's less than 2, it's just 1, which is encoded by a single x. So, so this function allocates a lot of memory and runs pretty slowly, but it serves my purpose to sort of illustrate what a real. It's not far off some real programs that I've come across. I might say something rude about JavaScript if I'm not careful. Here's my Grafana dashboard. So this is what happened when I ran this function with no special treatment, and so I call it with this. Oh, it just obscured itself. I call it with the Hey utility, Hey, from that was written by Jana Dogan. It's like curl essentially, but it calls whatever you're trying to. Instead of curling it once, it curls it like thousands of times and across many Go routines in parallel. So I called it a lot of times in parallel for 30 seconds. And this is the kind of thing I watch, in real life. The latency of the requests was kind of hovering around 55 milliseconds. So that's usually the thing I'm trying to make faster in real life, in my day-to-day work, trying to bring the latency down. The whole program was running in about 100 meg, peaks at about 100 meg, but it was garbage collecting 150 times a second. You do not want your program to garbage collect 150 times a second. You don't want your program to garbage collect 20 times a second, right? Like once a second is fine. Maybe twice, maybe, You do not want the garbage collector to run 150 times a second. Trust me. Okay, so this is where people turn to techniques like heap ballast, because they say to themselves, well, shit, I've got like more than 100 meg, I've got gigs on this machine. Like, just use a bigger heap, slow down the garbage collection. Okay, so let's do that. Let's give it a 100 megabyte heap ballast. So walk through it. So this was like the previous trace, and I stopped and restarted the program. And it starts off at 100 megabytes because that's what I've allocated, my kind of fake ballast allocation. This, by the way, I tried to kind of visualize the sawtooth for real, but it's too fast. It's like, even now, it's going at like 30 times a second. It's too fast for me to kind of visualize it with these tools. So it sort of looks a bit squiggly, but that's what's happening, that sawtooth. It just, sampling error makes it look like a squiggle. So we made the heap bigger with a heap ballast. We slowed down the garbage collector from 150 times a second to 30 times a second. Only at the cost of 100 megabytes of memory, right? Like virtually nothing. And the latency came down. So the latency was hovering about sort of 55 before. Now it's below 40 most of the time. So big win. You know, heap ballast is good. Heap ballast works. It's just a bit dumb that you have to fool the garbage collector. Okay, so what are we going to do instead? The soft memory limit. Who's heard of the soft memory limit in Go 1.19? Oh, again, only 5% of the audience have the strength to raise their hand at this point. So what is this? So what I said you couldn't do before is just kind of ask the Go runtime to use a bigger heap. You can do that now. You can set a soft memory limit. If you just set the soft memory limit, my sample program doesn't behave any different because the normal thing is the limit is bringing down the max size of the heap. What I want to do is make the heap bigger. So I have to make two settings. So this is the really obscure thing, right? If you say go GC equals off, so what that used to mean was never garbage collect, and they changed it, like they lied to you. This is a lie. Go GC equals off when set together with a memory limit. What it means is go up to that limit and then garbage collect. Well, actually, it's much cleverer than that. It tries to predict when it's going to hit the limit. It's garbage collecting in the background to try and come in below the limit. Anyway, so do this one instead. If you are in this situation, that you have a program that's using a lot of memory allocation, the heap is not very big. You could spend a little bit more memory, slow down garbage collection a lot, make your program run faster. So my benchmark, just sort of compare. I mean, it's a little bit hard to see, but the Go mem limit one is less peaky, just a little bit. It's a little bit better. It has the same kind of behavior that it goes up to the 200 meg, and kind of bounces around very rapidly. It's still garbage collecting like 30 times a second. It's still doing a lot of work. And one other interesting thing, like when the program finished, so the previous examples, they kind of come down, right, after a while. The garbage collector in normal circumstances will run when it approaches its target or after 2 minutes. That's hard-coded. 2 minutes is the maximum it will go without garbage collecting. But if you say go GC equals off, it will run and run and run, and when it finally gets towards the target, which based on that trace is going to be in about 3 hours, then it will garbage collect. But that's the kind of the one difference. The line never comes down effectively when you use the soft memory limit and go GC equals off. So that's all I came to say. Takeaways. The slice thing, casting a slice to an interface will allocate. Casting a slice value to an interface value, right? Because I fixed it by making it a pointer, by taking the address of the thing instead of, which was the same trick I pulled. I don't have a lot of tricks, right? I take a pointer to the thing and it goes faster. That's what I do. Heap allocation is costly in ways that you might not think. And it's almost always more costly than you thought it was. Generic methods like thing.thing are not fast. I should stress, I'm talking about Go as I find it today. So Go 1.19, which I just started using, Go 1.18 was very much the same. But the soft memory limit is only in 1.19. Go has been like this for a year or two, but it will change. right? So if you're watching the video in 2030 or something like that, most likely this advice doesn't apply to you. Sorry, I should have said this at the beginning, right? But only for the people in 2030. So the people in this room using the Go we have today, this advice applies to you. It will change over time. I'm talking about incidental details of the implementation, and these are not kind of fixed rules. And again, referring to the previous talk, which was about TinyGo, is a different implementation of Go. So if you happen to be using a different implementation of Go than the one I'm using, which I download from the Go project, again, it will work differently. Heap ballast, we loved it. It was good. It has to go. Heap ballast is a really, really dumb thing to have to do. And now we don't have to do it. We can do go mem limit. But you must also say go GC equals off. So I'm done.